In this video, I'm going to show how to set up an FSI problem using the ICFD solver in LS-DYNA. Now, the first thing to do would be to make sure that the pure CFD problem runs. In our case, this would be the classic flow on the cylinder, which we have studied and shown in a previous video. So once we have made sure that the input deck is correct on the CFD side, the second step would be to make sure that the input deck is also correct on the structural side. So in our case, we're going to use this 2D mesh of a cylinder, which is going to oscillate vertically, which means that it's got a boundary prescribed velocity or motion somewhere. So once we have made sure that the two problems, both the CFD problem and the the solid mechanics problems, that they both run independently, we can start to think about FSI. One way of doing it, which I like, is that you could set up a new keyword file which would include on the one hand the fluid input deck and on the other the structural input deck. This way you keep both things separately and it's just easier to handle. So if I run this problem as is, I'll get something like this. With the fluid mesh, the structural mesh, and if I start to animate it, the solid keeps oscillating and the fluid completely ignores whatever the solid is doing and keeps solving the same exact flow on the cylinder case. And this is normal. Remember, those two solvers are completely independent within DYNA, and both the CFD and the solid mechanics solver can run as standalone solvers. Now, if I want to trigger the FSI, I need to add a few keywords. The first keyword that I'm going to add is going to be called ICFD control FSI. This keyword will specify the different coupling directions. If I want the two solvers to talk to each other, or only one talking to the other without the other passing any information. Since I want to solve the complete FSI problem, I'm going to leave it by default, which is 0. The second flag, which I have to the second keyword, which I have to define is called ICFD Boundary FSI. And in this keyword, I'm going to specify which of the surface meshes are going to interact with the structure. In our case, if you remember the classic flow on the cylinder case which we studied, this was part number 4. So surface part number 4. So now our FSI problem is ready to run. If I run this case, I will get something like this, where suddenly you can see here the fluid mesh following the structure's displacements. Okay, this is called an ALE approach. ALE in the sense that the mesh follows a Lagrangian motion while the fluid flows through it in a Eulerian way. So if I go again, if I look at that, okay, so now I see that indeed this fluid takes into account the solid's position. But not only that, but it seems that also the fluid has an effect on the solid. Before it was only oscillating vertically. Now it seems that indeed the fluid is pushing the solid to the right. So now we have solved our first FSI problem. As you can see, it was rather painless. The second step, which I want to show you, is what happens if we change the coupling direction here and we put in 1. So if I put in 1 here, only the structure will communicate its position and velocity to the fluid. The fluid, whatever the fluid solves, it won't pass anything back to the structure. So this is called a one-way coupling. So if I do something like this, I get, as a result, something like that. When I try to animate here, and if I display the velocities, I can see that the fluid still takes into account the solid's movement, but if I look at the solid, it only translates in the y direction. There is no movement in the x direction. This is because the fluid now no longer has any influence on the solid anymore. This would be a coupling direction 1. Okay. Before we move on to something else, I just quickly want to show you something. If I change my boundary condition and have the solid, instead of having it translating in the y direction, I'm going to have this cylinder spinning, rotating. So let's see what happens to the mesh in those cases. if I keep something like that, see, oh, now we see our solid that starts spinning, and the fluid mesh follows, well, the solid's rotation, and so also starts to spin, and of course it starts to distort more and more until you get this very ugly behavior, but still the solver does not crash. And once something happens, the solver will automatically remesh, start deforming again, remesh, start deforming again, and so on and so on. So obviously in those cases the solution is probably not to be trusted. If you look at it, you can see here the very strong mesh effects. But nonetheless, it's interesting to see that the solver can handle this. So by default, what's the criteria? When does the solver apply this remeshing? So the solver by default will only remesh if an element gets inverted. So you can see here that the deformation that the solver can tolerate before applying a remeshing can be pretty high. Okay, so, and which is good, because remeshing is not something that you wouldn't want to happen too often for two reasons. The first reason is that remeshing is only done on one CPU. So when you're doing MPP analysis, which I would recommend for the ICFD solver, then this would break your scalability and increase your calculation time. And the second thing is that obviously when there's a remeshing, the solver has to communicate the values of pressure from the old nodes to the new nodes, and you may have some jumps, numerical jumps in the results. Nothing too bad, but you just have to be aware of it. So for those reasons, remeshing is avoided, but as you can see in a case like that, well, we'd like the solver to remesh a little bit more often than only when an element gets distorted. We'd like the solver to remesh. Well, if the mesh gets too distorted, please remesh. So there's a keyword. The keyword for that is called ICFD control adapt. Let me open here the right file. There you go. So here it's called ICFD control adapt size. And if I put the first flag to 1, it means that I'm going to ask the solver to also do a remeshing based on certain quality criteria of the elements, global criteria, local criteria. So now this is the same case, only I've triggered the ICFD control adapt button. If I do that and animate it again, you'll see here that the remeshing seems to happen way more often and way sooner than before. Okay, and indeed, if I look here at the ICFD mesh statistics files, this tells me each time the solver applies a new remeshing, it dumps one of those files, which gives me a bunch of information on the mesh quality and the number of nodes used, and so on and so on. So in our previous case, where we hadn't triggered this button, it showed here that it applied the remeshing only twice. Here we have the initial mesh, and then we have the other two cases, whereas once we have triggered adaptivity, it has done way more remeshing. So again, this is a pretty useful tool to be used in moderation, of course, only in cases when this is really necessary, since remeshing will increase your calculation time. Now there's something which I want to show you. I'd like to show you to the limits of the present FSI coupling. By default, if you use the explicit solver in LS-DYNA, you do what is called loose coupling. It's also known by the names of explicit coupling or weak coupling. Basically what happens, if you look at the theory manual of the ICFD solver, this is how the loose coupling works. You have the ICFD solver that will do one step. Since it's implicit, it's got a very high time step, and once it has reached, it has completed its time step, it will wait. It will wait for what? It will wait for the structural solver to catch up. Okay, so the structural solver running in explicit, so having a very small time step, will do all those little time steps, and in the meantime it'll do a force interpolation of the results of the pressure results from the ICFD solver, and use this as an exterior load and solve, and so on and so on and so on, until it has passed the time of the ICFD solver, and at this point it will feed back the displacements and the velocity back to the fluid. So as you can see here, the two solvers run completely independently. They both have the independent time steps, and they just pass information one to the other. So this type of coupling is referred as loose coupling, and it works in quite a few cases, especially in cases where the solid is very rigid or very heavy compared to the fluid. Usually it's going to be air around steel, those kind of things. Now I'm going to show you one of the limits of loose coupling. Such limits, they can happen when you have strong deformation, but very usually with materials that are very light, like gum and rubber, where the density of the material is very close to the density of the structure. So if I look at my structural input deck, I see that I have a density of the material of 1000, and by default the fluid input deck had a density of 1 here. But if I change this to a density of 1000, namely that both the structure and the fluid have very similar, or in this case the same density, now let's see what happens. I run the same case again, and if I try to animate it, okay, so far so good, it goes to the right, it's normal, it's a lot lighter, the solid is a lot lighter now compared to the fluid. Okay, so far so good. But, whoa, what happens after a certain time? Be easier if I look at the mesh here. Okay. So at first the solid seems to follow a correct path, going to the right, being blown by the wind, but after a certain point it seems like it jumps back to the left, and then if I keep on animating, it even completely destroys the mesh and goes completely out of it. What has happened here is that you have just seen the limits of loose coupling. The cylinder entered an oscillating mode where it goes from the right and back to the left, and so on until it completely comes out of the mesh. And this is normal. This is a fundamental limit of loose coupling. If you want to solve such an application with the solid having a density that's very close to the one of the fluid, you have to do strong coupling. Now, in order to do strong coupling, if you look again at the theory manual, what happens for strong coupling is that the fluid will solve, feed its forces to the mechanical solver, which will also solve, feed it back to the solver, but instead of moving to the next time step, it's going to enter into a convergence procedure. Okay, so both the two solvers are going to keep exchanging information until they both agree and have found a common solution before moving on to the next time step. Now, since the ICFD solver has very big time steps, and now for strong coupling the two solvers have to advance at the same time, well, on the solid mechanics part, you also need to have a very high time step. So the only way to trigger strong FSI coupling with an ICFD solver is if you use an implicit solver. So in our case, it will be the implicit solver of DYNA. So here are some classic keywords that are related to the DYNA implicit solver. There's usually implicit in the name, and so on and so on. But on the fluid part, there's no further modification of the input deck needed. Basically, if you use the explicit solid mechanics solver, you're automatically going to trigger loose coupling, and if you use the implicit solid mechanics solver, you will automatically trigger strong coupling, because there is no other way. There's no way to do otherwise. So now, after triggering strong coupling, if I start running the case, I will see now that it behaves in a much better way, and it has a more consistent behavior. Okay. So this was here. I wanted to show you in this video how to set up a problem, classic FSI problem, but also show you the limits of loose coupling and showing you what the FSI strong coupling can bring. Other examples of applications for strong coupling. This is the Turek FSI2 benchmark. Is a very classic problem. This is shown whenever you want to prove your strong FSI coupling capabilities. This is the validation case that is being studied here. We have a very flexible flap that starts to enter in oscillating mode, so it's a very highly nonlinear FSI problem. Another validation example would be classic sloshing case, where you have again a very flexible flap that's oscillating in it. Other applications would be for hard valves, as you can see here, and so on and so on. So the objective here is to open a new range of applications to users who want to do, on the one hand, CFD, but who also want to do FSI. So thank you for listening, and see you in a new video.